Okay, we've talked about multiplication. We've talked about permutations. We've talked about permutations of subsets. Now let's look at another example, and that is when we have similar objects. So in the previous example, I gave you the circuit board, and I said we have 4 components to connect to the circuit board, but they're 4 different components. But now the question would be, what happens if the 4 components are indistinguishable? In other words, I'm going to write a little bit smaller because I only have 3 sheets of paper left. But in other words, we have our circuit board with 8 slots. And you want to connect 4 components to each of those slots, but this time, the 4 components are indistinguishable. They're the same. We can call them similar objects. In other words, if component 1 and component is here, and component 2 is here, it doesn't matter if component 2 is here, component 1 is here. It's the same, right? Because they are, we treat them as the same. In this case, we say that they are similar objects. My first question would be, in the last example, we said that there were 1,680, so 1,680 possible combinations if the components are different. If the components are all the same, we still have 4 components, so there's still 4 different slots that need to be filled. Do you think we'll have more or less possibilities?
Wait, so last time it mattered the order they went in?
Last time, the order mattered because each component was different. This was component 1, this is 2, this is 3, this is 4, different components, and that's why we had 1,680. This time, they're all the same component. It's 4 components, but they're all the same. Order doesn't matter here. So less, right? Good. We'll have less possibilities. And the calculation is called a permutation of a similar object. There's no variable assigned to it, but essentially what happens is we need to figure out what these similar objects are. Now, you may need to maybe analyze this a little bit. Oh, I just saw a message. Yeah, less does not matter. If you see a message that, just maybe give me a heads up to look at the chat. Okay. So in this case, we need to know what those similar objects are. Now remember, what you want in the end is your ice cream, right? So regardless of what toppings you're choosing, the final result is not the toppings or the circuit board itself, it's going to be the combination of both of them. So in this case, my similar objects, I can look at my 8 components and my 8 slots, and I can say that 4 slots are going to be, connected slots. In other words, they're going to have a component attached to it. So that's 4. So if 4 slots are connected slots, how many slots are unconnected slots? 4. Because we have 4 of these are going to be with a component, the other 4 are going to be empty. So in this case, we have 2 groups of similar objects. You know, 2 groups. One group is the slots with the connection. The other group is the slots with no connection. And in this case, the calculation is going to be the total number of outcomes or possibilities over the factorial of the different groups. Now this does not really help because we have 8, 4, 4, that doesn't help. So let me just generalize it. It's going to be my total number of outcomes n over the number of possibilities in each group of similar objects. So n1, n2, all the way up to nk, where k is the group of similar objects. In this case, we have 2 groups. My first group has 4 objects, so it's 4 factorial. My second group has 4 objects, so it's 4 factorial. There's no third or fourth group, so that's all it is. This is not a very good example just because we want to make sure it's generalized very well. So let me do a different one. And this time, let's say that you're managing a hospital schedule. You're managing the usage of an operating room for a hospital. And just to give you something very generalized, let's say you have to schedule in one day. That operating room needs to go through 3 knee surgeries. And let's just call them K. And you also need to do 2 hip surgeries. Call those H. Now the knee surgeries are all going to be done by the same doctor, so we're going to treat them as similar objects. It's like, it doesn't matter which knee surgery goes first, it's all pretty much the same. The 2 hip surgeries are going to be done by another doctor. So again, it doesn't matter the order of the hip surgeries themselves, because they'll be done by the same doctor. Now the question is, you will need to arrange the schedule for your operating room. In other words, you need to arrange the schedule for your two doctors. So what are the possible combinations or possible permutations of this schedule? In other words, you have 3 knee surgeries, you have 2 hip surgeries, but you don't care about the individual knee surgeries. You care that it's a knee or hip. But when it's a knee, it's the same doctor regardless, so you don't care which of the 3 knees goes first. So what are the possible sequences that you can schedule the 3 knee surgeries and 2 hip surgeries in? Just give me one example.
The doctor.
Okay, so have the knee doctor do all his 3 surgeries at once, and then the hip doctor do all his 2 surgeries. Okay, you could do that. You're civil engineering students, right? Okay, so what else?
Knee, hip, knee, hip, knee.
Okay, you can give them all a break in between. What else?
You can start with the hip.
And just like this. Good, what else?
Hip,
I
knee,
should have
hip,
chosen a
knee.
different variable. Now that I realize. Anything else?
2 knees, 2 hip, 1 knee.
2 knees, 2 hips, 1 knee, good.
Hip, knee, knee.
Hip, knee, knee, good. What else? There's more.
Knee,
There's
hip,
more.
hip, knee, knee.
Can you say that again?
Knee, hip, hip, knee.
Hip, hip, knee, knee.
Hip, what?
No, I was just trying to repeat.
Oh, okay, sorry.
Like it's
What
called
else?
that just one sort of talking. Hip, knee, hip.
Hip, knee, hip. Hip, knee. I think that one was already said, yeah? Just a hint, you're missing 3.
Hip, knee, hip, knee,
Hip, knee,
hip, knee.
hip, knee. Okay. You're missing 2.
Knee, hip, knee. Is that one that's out there?
Knee, hip, it's already there.
Oh,
Knee, hip, no, wait, no.
knee, hip, knee.
What?
Is that up there?
Knee, hip, knee is already here.
Okay.
Knee, hip, knee, hip.
Okay, that's not there.
That's hard.
Good. Knee, hip, knee, that's already there. It's the second one.
2 more.
One more. One more. Come on, hospital schedulers.
Knee, hip, knee, hip.
What?
Knee, hip, knee, hip.
I don't see that there. Wow, good. Knee, hip, good. We got them, all 10. But how do I know there's 10? Well, exactly, right? We go back to our similar objects permutation, and we say that we have the total number of possibilities over the number of elements in each of these similar groups. So how can I take this generalized equation and apply it to this example? What would that look like? What's the total number of surgeries? How many surgeries? 5, right? 3 knees, 2 hips.
3 times 2.
No, it's 3 plus 2, right? 5 surgeries, good. And then I would divide it by the total number of elements in each group of similar objects. So the first group of similar objects is, let's say, knee surgeries. How many elements there? The second group of similar objects are hip surgeries. How many elements there? 2. So 5 factorial divided by 3 factorial divided by 2 factorial gives us, I mean, you know it's going to be 10, but let's see. It's 20 divided by 2, 10. Good. Of course, you're probably not going to run into this unless you switch fields, which is fine, perfectly fine. But the idea is to be able to recognize when to group things as or into similar objects. If you can do that, we will be good. Because if you can group your elements into similar objects, where you can say, well, order doesn't really matter here, then your calculations will be a little bit easier. Good. Very good. There's another example with a printed circuit board. When I get it in class, it's similar to what I did earlier, but just with different numbers. It's in the notes. You can try it out yourselves if you want to practice. Same thing we did in class, just with different numbers. Okay. Let's review or introduce a very, very important mathematical operator known as the binomial coefficient. I say very important because you're going to see it in class a lot. And since you're going to see it in class a lot, I think it's better that we just, get familiarized with it a little bit before we go and use it. Has anybody heard of the binomial coefficient before? It's okay if you haven't. It's not your fault, right? So, anybody heard of it before? No? Okay, good. The binomial coefficient, in a future class, we're going to explain why it's called binomial coefficient and where it comes from. It's actually related to binomial expansion, which is a series. But, we'll talk about that later. I think for now, what's important to know is how we use it. So, the binomial coefficient is going to help us to choose our elements from a set of n elements. I know using variables in sentences is not very helpful. So, if we have n total elements, let's say n possibilities, and we want to choose r of those possibilities, the binomial coefficient, which we express as n choose r. So we have n total possibilities, we want to choose r of those. All the binomial coefficient does is it tells us how many possibilities are there. How many possible ways can you choose r elements from a larger group of n elements. And that's calculated by taking n factorial and dividing it by r factorial times n minus r factorial. Okay, that's all it is. Now you may not realize it, but the binomial coefficient really it's a way of expressing a permutation of similar objects as long as you have two groups only. Because notice that here we had eight total slots, and we divided them into two groups. One group was 4, the other group has to be, well, a minus 1. And that's exactly what the binomial coefficient is telling us. The binomial coefficient is telling us how many permutations of similar objects do we have if we only have two groups. Bi, it means 2, so we only have two groups. Now, the binomial coefficient, like I said, very important. It's going to show up not just here in counting, but it's going to show up in different probability distributions. It's going to show up in different things that we're going to learn later in this class. But typically, the result of a binomial coefficient is what we call a combination. The book sometimes writes it as C of NR, but I don't like using C of NR because nowhere else is that used. So n choose R is the most common way of seeing the binomial coefficient. When I say how many combinations of blah, I'm asking you to use the binomial coefficient. Okay? When I say how many permutations of blah, I'm asking you to either do permutations of similar objects, permutations of subsets. So that one's a little bit trickier. But when I say a combination, then by default I am referring to the binomial coefficient. Okay? Very important that you understand how to use it. I know there's calculators online that you can just Google binomial coefficient calculator, right? But try to get a little bit familiarized with it, because if you get familiarized with it, then at least you'll have a more or less of an idea of what your number is going to look like, what the magnitude of your number is going to be in. It's going to be like. So learn how to use the binomial coefficient. Maybe do some hand calculations just so you can get used to the equation behind it. That being said, I guess we should just do an example, just to know that we're okay with what we're talking about. And let's say, oh, by the way, just a note, I'm using R because the textbook always uses R as the subset variable, but everywhere else, especially in non-engineering statistics, the variable is actually K. So if you look at binomial coefficient, you'll see n choose K, right? Instead of n choose R. Don't be afraid, it's just variables, right? But it's just that for some reason in engineering we use R more, but outside of engineering we use the variable K more. I really don't know why. And I'm trying to go by the book, so just because it's what you're using as well. Okay? But yeah, let's say you have a set of 3 parts. I don't know, maybe you can say 2 tools, and you want to choose 2 of those tools. How many combinations do you have? You have 3 tools, you want to choose 2 of those. How many combinations? What would you do to try to solve this? 3. Okay, how do we get to that number?
I'll put the plug in.
Okay. So what are we looking for? We have 3 parts or
Choose
tools.
2.
We want to choose 2. So our operation is going to be 3 choose 2. Then we just write down the equation. And you'll see that this actually lands us at 3. Okay. You got 3 times 2 factorial divided by 2 factorial. This is just 1, so it just gives me 3. Okay. Let's make it a little bit more interesting. Anybody know how to play poker here? More or less?
Yep.
Okay. How many cards does a standard deck have?
52.
52, good. Awesome. How many cards is your hand at poker? How many do you choose at a time?
2 in your hand and then 5 on the board.
5 on the board, good. Awesome. How many possible combinations are there? Like you have your 52 cards, right? If you have 5, right, you choose 5 from those on the board. How many ways, how many possible combinations of those 5 can you have?
Well, like every player has 2 in their hands. That takes.
Let's say it's just you. Otherwise, it's just gonna make it a little bit harder.
Right.
Just you. You don't have to give me, don't try to calculate it on your mind. Just, how would you go about finding that number?
What would you just do? 52 on top and then 5 and 52 minus 5.
So 52. And how many do I choose?
5.
5. Okay. That's it. I mean, you can calculate it, give me the number, right? But what I want to make sure is that you know that this is the operation you're gonna have to do. Okay. 52 choose 5. You're gonna calculate it yourself? Okay, that's fine. We can do that. Let's see. We got 5. 52 minus 5. We have 52, which gives us. I don't think you're gonna find this in your online calculators because some of the online calculators are not very good. How many possible combinations?
Someone got on the board.
Oh, sorry, let's see it. Thank you. So 2,598,960 possible combinations. That is absolutely right. I was toying with an idea, which I don't think it's mature enough for this class. I don't mean mature in terms of immaturity. I mean mature in terms of how it's developed. But I was thinking of selecting, like, is there a grade for participation here on the syllabus? I don't know if there is.
Can't remember.
Well, if there is, I was thinking of gambling that grade. And when you learn statistics, you'll know what you want to gamble for, right? And to increase your chances of getting that grade. But I think that would be what do you call that? An ethical nightmare, right? Especially for the students that don't win. Like, oh, that's not fair. I did all my homework. I just didn't gamble correctly.
We still play chess for a letter grade?
What?
We still play chess for a letter grade?
The thing is that nobody can beat me. It's like Mario Kart, right? I used to play Mario Kart against my students in exchange for an A, but nobody can beat me. I mean, that's why I do it. I'm never gonna give it an A, right? But I wouldn't do it unless I know that I can beat them.
If you play for FIFA, I must play you for the whole grade.
FIFA?
Yeah.
You know I am.
I don't care who you are. I play for the whole grade.
You know I'm Hispanic, right? So I'll put you soccer
Too.
Hispanic.
Yeah, I'll play you chess.
Chess?
Yeah, I got you.
Got it.
You play hearts?
What?
Hearts?
No,
I'll play hearts. It's fun.
I don't play. My wife plays. My wife is better at me like card games. I'm good at chess. I'm good at soccer, but not FIFA. Just like soccer.
Oh, we can play over that too.
Nah, I'm almost 30 years old, man. It's been a while. Okay. Let's go over some definitions. We've done some examples. That's good. Let's talk a little bit about some definitions. I'm going to use these words probably throughout the rest of the class and throughout the rest of the semester. When I say choose, like you're choosing this, you're choosing that, you're selecting this, there's actually a technical term for that, and that is sampling. So when I'm saying choose this, choose that, really what I'm asking for you to do is to sample something. There you go. Sampling, right, the technical definition would be to select an item from a set of more items. Of course, there are some mathematical limitations. For example, you have a set of 10 items. The maximum number of items you can sample is 10. I can't say choose 15 out of these 10 items, right? So sampling is, just choosing one or more items from a set of more items than that number, or the same number, okay? Now there's two types of sampling. We have sampling with replacement. And we have sampling without replacement. I'll explain what those mean in a second. So sampling with replacement means that you choose an item from your big batch of items, and then you place it back and choose again. Sampling without replacement is that you choose an item, and then you don't place it back, you choose another one without placing your original item back. How does this work? Well, we have a toolbox with 10 tools on the box, and you want to choose one box. If you're doing sampling with replacement, and you choose a tool, how many tools are going to be in the box when you choose your second tool? If you're doing sampling with replacement, 10, because you're placing the tool back and you're choosing again. But if you're doing sampling without replacement, how many tools will be in your box? 9, good. If you're doing sampling with replacement, how many times can you sample out of that box?
As many as you need.
As many as you need. If you're doing sampling without replacement, how many times can you sample out of that box? 10, right? Because at the end, you'll have no tools to sample. Good. Does that make sense? It's important because, we're not going to be literally picking things and putting them back. So what is the difference between sampling and sampling without? Oh, sampling is just the general idea of picking something, of choosing an element. That's it. So there's two types of sampling. Right? There's sampling with replacement, and then there's sampling without replacement. That's all it is. But sampling is kind of like the idea of selecting an item. Okay. So the reason this is important is because sometimes we can do some sampling with replacement, and you'll notice that it's not going to be about choosing tools. Or when you're, especially as a civil engineer, you want to use statistics, then you will most likely end up in the transportation engineering field, the traffic engineering field, or in the hydrology field. But statistical hydrology is a different monster altogether. But the idea is that sometimes your sampling will be with replacement, sometimes your sampling will be without replacement. Think of something like the day-to-day number of cars on a highway. Your cars, they drive through their highway to go to work, they drive back to go home, and it's kind of like replacement because the next day then they're driving again to the same highway. That's how it is, right? Other times you're going to have sampling without replacement. So you can think of something like, I should have thought of a transportation engineering example. I guess that's more relevant to you. I'll think of one, or you can think of one. But anyway, the idea is you're going to have to choose, or you're going to have to determine whether your sampling will be made with replacement or without replacement. Okay? Let's apply now all this to a small manufacturing problem. This problem is more or less from the textbook, although I've been sometimes I take textbook problems and I make them just a little bit different so they can match what I'm actually teaching here. But let's say you have a bin with 50 parts. You have your little bin. What's going on? I'm not seeing straight here. You have 50 parts inside this bin. Out of those 50 parts, 3 are defective. How many are not defective?
47.
Good job. Good, 50 total, 47 are defective, 3 are defective. If I want to choose, okay, I want to sample, let me use the technical term. I want to sample 6 parts without replacement. In other words, I pick one, I don't put it back, I pick another one, another one, another one. How many different possible samples do I have that contain exactly 2 defective parts? Let me just break that down. So sample 6 parts, okay, without replacement. So how many of your samples, of your 6-part combinations, are there that contain exactly 2 defective parts?
So like you take 6 out at a time,
It's like if you take 6 out at a time, yeah.
and then 2 of them.
And then out of those 6, 2 are defective. So if you were to do this for 6 at a time, how many possible, or how many of those combinations would actually have 2 defective samples?
Is 2 like minimum, 2 like that?
Exactly 2. Good clarification. Exactly 2 defective parts. Why am I not writing straight? So you don't see it here, but my paper is actually like this. Even though this looks straight right now, even though this looks straight right now, I'm actually pointing that way, which I don't know what's wrong here. But anyway, what are we looking for here? Like, is there a way to maybe express this in terms of any of the things we talked about earlier?
Well, I think
Permutations, okay, we could be looking at a permutation. I don't think so.
Isn't it just one because you take
Outcome.
2 and then
What?
you don't have
Outcome.
Yeah, different outcomes, yeah. But then how? Like, are we looking at permutation, a combination, similar objects, subsets, yeah?
This is without replacing?
Without replacement.
I'm assuming that every part is unique, is it not?
No. So we have 47 non-defective parts, 3 defective parts. Other than that, those are the only 2 differences that matter. Really good clarification here, right?
Mhm.
47 parts are not defective. We don't care what parts they are, right? We only care about whether they're defective or not defective.
And we're looking for a combination.
Back, wouldn't it just be the one outcome where you have 2?
Well, you have different possible combinations, right? You take 6 parts out, right? And remember, your sampling consists of getting 6 parts without replacement. You get one, you get another one, you get another one, you get another one, you get another one. So if you each have your 50 your bins with 50 items, and you each take a sample of 6, you're not going to have the same exact sample, right?
Well,
So
are we
that's why.
it feels like we're just basically looking for how many ways we can get the 3. Is that
Yep.
right? Yeah, okay.
How many actually we can get the 2? Right, the 2
Well,
different
two out of the 3, yeah.
So let's break this down a little bit, because this I like this example because it doesn't really give you things very directly. You will need to do a little bit of analysis to break it down. So the first thing I'd like to ask you is, how many defective parts are going to be there in your sample?
Just
2, right?
Yeah, 2.
But then how many defective parts are there in total?
3.
Okay, so first I want to know how many possible combinations of defective parts I have. In other words, out of my 3 total defective parts, I would like to choose 2 of those. How much is that? We've already done 3 choose 2 before. What's 3 choose 2? 3, good. Good. Now here's the thing. Each sample has 6 parts. We already said that we're sampling 6 parts without replacement. Out of those 6, how many are defective?
2.
How many are not defective?
4.
Okay,
4.
so out of the 47 non-defective parts, how many should we choose for each sample? 4, good. So 47, choose 4. Okay. You can do the math. I have it here. It's about 178,365. So we have 3 different possible ways to select my 2 defective parts, and 178,000 ways to select my non-defective parts. But of course, our sample consists of both of them. And here comes the easy one. So if we divide this experiment into 2 steps, selecting 2 defective parts and selecting 4 non-defective parts, how can we get the combined outcome of the different steps? If you flip a coin and then you flip it again and then you flip it again, what do we do?
178.
Multiply times 3.
You multiply it, right? Remember, if you have different steps in your experiment and you just want to know the combined number of outcomes, you just multiply the outcomes in each step. So I know it's not really intuitive, or sorry, not as intuitive as what we've done before, but the idea is when you get something like this, sometimes it's a little bit helpful to split it up. In this case, telling me how many samples contain 2 defective parts is a little bit hard, but if I say, okay, let me break this experiment into 2 steps. Step number 1 is to choose my 2 defective parts. Step number 2 is to choose my 4 non-defective parts. Then my total number of outcomes is just the multiplication of the number of outcomes in each part of the experiment. So in this case, using multiplication, I get an answer of 178,000 times 3, that's 535,095. Okay? Break it down. I'm not going to expect you to start breaking things down right now. So we're still going to do some stuff where we kind of work on it together. But you'll notice that by the time we get to, let's say, the first exam or something, you may need to start breaking things down in order for you to actually be able to solve it. So in this case, don't think of it as selecting 6 parts. Think of it as first selecting your 2 defective parts, then selecting 4 non-defective parts. And think of it that way always. Like when I say, you know, when I ask you to give me the number of outcomes or the number of possible cold stone combinations, again, don't think of the whole ice cream as coming together at the same time. Think of it in terms of steps. First, I choose my flavor, my base flavor. Then I choose my topping. Then I choose my container, right? So always try to break things down into different little steps. We're doing really great on time, which that makes me very happy. We have a lot of material to cover. So, but before we end today, I do want to give you a sampling table, and it's actually in your notes, so you don't have to write it down. This table will be just for you to have as a reference. We're not going to derive everything, but essentially, I do want you to know that when you're sampling with replacement, and when you're sampling without replacement, there's actually 2 different ways you can find the number of outcomes. If my order doesn't matter, which is what we do in combinations, remember combinations is kind of like a permutation of similar objects with only 2 different groups. So if my order doesn't matter, and I'm sampling without replacement, then it's simply a combination, n choose R or n choose K. However, what happens if I'm sampling with replacement? In this case, it's actually going to be n plus R minus 1, choose R. And then, if my order matters, so in this case, we look at everything, every part as a unique part, then it'll be n to the power of R. And if it's without replacement, it'll be n factorial over n minus R factorial. You don't have to memorize this table. It would be helpful to have it as a reference so that when you are working on different examples, you can kind of choose for yourself. Or does order matter? Does order not matter? So order matters when each part is unique. Order doesn't matter when the parts are not unique, right? And then with replacement means that you place it back before selecting the next part. Yeah?
So for the last example, you said, I asked you that you said exactly 2. What if, how it would be different if we would say that minimum of 2 defective tools? Is it like?
We're going to look at that in the next class. It's a little bit more complicated. So in that case, what you have to look for is you're looking for a combination of n choose R, then you're looking for that times n choose R plus 1, R plus 2 until you get to n, right? So it's something that we're going to be looking at. It's actually a little bit easier if we see it in terms of continuous measurements, right? Because you can use these equations for that. But we're going to deal with this in the next class, okay? Your homework consists of 7 problems. Try to solve them. They're all about sample spaces and counting. They'll be expressed a little bit differently. I chose problems that have solutions. I'm not sure if the solutions are in the textbook or if they're online, but you should have, if you have the textbook, you should have access to the online solution. So all the problems I chose have some solutions attached to them, either in the textbook or online. So you should be able to see the solutions to kind of have an idea of how to solve them. If you can't, just let me know if there's a problem that we want to work through, and we can try to work through some of the harder ones in class. Not all classes are going to be this, 1 submission per group? Yes, 1 submission per group. Not all classes are going to be this short. Sometimes our classes are going to take the full 2 hours and 45 minutes. Sometimes, like now, it'll be about 2 hours and 15 minutes, 2.5 hours or so. Because this is the first material, it's kind of relaxed. The class is going to get harder, and then it's going to get easier at the end. So it's kind of like a little bell curve, where the hardest material will be at the middle of the summer. Okay? Any questions? No? All right, then I will see you on Wednesday online. We'll meet Wednesday online.